A Sci Amazing Day Sci-Po, your Sci energetic teacher is here today for you to explore, discover, and enjoy life. Please allow me to be with you as you learn. Make sure you have your pen, your paper, and everything for this session. This is your teacher Richmond, and welcome to another Sci Wonderful episode.
Projectile motion using a water hose. If you take a garden hose and shoot the water at an angle, it's essentially projectile motion. Remember, as long as an object only has a gravitational force acting on, its motion will be projectile motion. If you consider each little water molecule in the stream, this isn't completely the case. The water molecule interacts with the rest of the water around it. However, most of these interactions add up in a way that they either cancel out or are negligible. In the end, you get the water that acts like projectile motion. For our activity, try this. If you don't want to pull out your hose, you can also do this with a cup or a can. Put a small hole near the bottom of the cap and then fill it with water. Observe what will happen next and answer the following questions. For number 1, what happens to the water inside the cup? Number 2, take your leaking cup of water and drop it. While falling, is there any water coming out of the hole? Why? For number 3, what is the common between the water hose and your setup? Cup or can with a small hole near the bottom filled with water.
The study of projectile is an extension of the study of motion in a straight line. The object may chase a curved path, hence, motion is in a plane. To make our discussion simpler, we will not consider air resistance and challenge the value of gravity with varying altitudes. A projectile is a body which is given an initial velocity and is allowed to move under the sole influence of gravity. The path followed by a projectile is called trajectory. We shall consider two types of projectiles. First, a body shown horizontally with an initial velocity and goes downward along a curved path. Examples of these are bullet, far from the gun, and baseballs. Second, a body thrown with an initial velocity at an angle from the horizontal. Example of these are shell fired from cannonballs and golf balls. Let us tackle the first type and see how the motion behaves. Consider that the fact that the initial velocity or VI is constant and that object is under two simultaneous motion, one horizontal on account of its initial velocity and the other vertical on account of the influence of gravity. This means that at any point in the trajectory, the initial velocity is resolved in two components, namely the horizontal component or Vx and the vertical component Vy. Take note that the Vx is equal to Vy, hence the horizontal acceleration is 0. For example, Ex is equal to 0. The component Vy is directed downward, hence its acceleration is the value of gravity. For example, Ay is equal to g at any time. Hence,
V sub y is equal to 0 plus acceleration due to gravity times time.
the actual velocity, or v with an arrow on top, is the resultant of the two components, which is obtained by the vector addition. Its direction is tangent to the path of the projectile. The horizontal displacement is signified with t with an arrow on top, and the vertical displacement is h.
At any time, horizontal component is equal to initial velocity, and vertical component is equal to acceleration due to gravity times time. To compute for the actual velocity, square root of horizontal component raised to 2 plus vertical component raised to 2, or actual velocity is equal to square root of initial velocity raised to 2 plus acceleration due to gravity times time raised to 2. To compute for the tangent theta, vertical component all over horizontal component, or tangent theta is equal to acceleration due to gravity times time all over initial velocity. The formula for the horizontal displacement is horizontal component times time, or horizontal displacement is equal to initial velocity times time. Lastly, the vertical displacement can be computed by 1/2 times acceleration due to gravity times time raised to 2, or vertical displacement is equal to acceleration due to gravity times distance raised to 2 all over 2 times initial velocity raised to 2.
For example, a stone is thrown horizontally with a velocity of 40 meters per second from the top of a building. Find its velocity and displacement after 3 seconds.
But first, let us identify the given in the problem. Initial velocity is equal to 40 meters per second, which is also your horizontal component, and your t is equal to 3 seconds. Find for actual velocity, horizontal displacement, and vertical displacement. For letter A, since we need the value of vertical component to solve for the actual velocity, we need first to identify the value of v sub y, or the vertical component. Since it was discussed a while ago that v sub y is equal to acceleration due to gravity times time, we are going to use this formula to find for the value of v sub y. Substituting the given and the constant acceleration due to gravity, v sub y is equal to 9.8 meters per square second times 3 is equal to 29.4 meters per second. Since we already identified the value of v sub y, we can now solve for the actual velocity. Actual velocity is equal to the square root of 40 meters per second raised to 2 plus 29.4 meters per second raised to 2 is equal to 49.6 meters per second. To find for the horizontal displacement for letter B, we will use the formula initial velocity times time. Substituting the given to the formula, 40 meters per second times 3 is equal to 120 meters. For letter C, to find for the vertical displacement, we will use the formula 1/2 times acceleration due to gravity times time raised to 2. Substituting the given and the constant acceleration due to gravity, 1/2 times 9.8 meters per square second times 3 seconds raised to 2 is equal to 44.1 meters.
Now, let us consider the second type of projectiles. And an object is thrown with an initial velocity at an angle from the horizontal, it will reach a point where the height is maximum and the vertical component Vy is equal to 0. After this, the object starts to move in a curved path downward, similar to the first type of projectile. The total horizontal displacement is called range and is denoted by r. Recall that we have discussed in our previous lessons, the horizontal and vertical components are obtained as follows. First, Vx is equal to V cosine theta, and Vy is equal to V sine theta. Throughout the flight, Vx remains the same. It is calculated with the formula Vx equals V naught cosine theta. At the initial velocity, or Vi, the vertical component is computed by the formula Vyi is equal to initial velocity sine theta. At any given time, the value of Vy can be computed by Vy is equal to initial y component minus gravity times time. Since initial y component is computed by the formula initial velocity sine theta, the formula to solve Vy is then Vy is equal to initial velocity sine theta minus the product of gravity and time. It is clear from here that Vy is decreasing until it attains a value 0 at B, reaching its maximum height. Maximum height can be computed by the formula maximum height is equal to initial velocity sine theta raised to 2 all over acceleration due to gravity. By some derivations, the total time flight t can be computed by the formula t is equal to 2 times initial velocity sine theta all over gravity. Since we already computed the total time flight, or t, we can now compute for the range, which can be computed by the formula r is equal to initial velocity cosine theta times t. To find the maximum value of the range, we have maximum range is equal to initial velocity raised to 2 all over gravity. And this is achieved when the projectile is released at 45 degrees from the horizontal. To explore more about this concept, let's have an activity. The objective of this activity, currently on an incline, is to capture a full trajectory of a projectile motion on an inclined surface. It also investigates the relationship between the angle of release and the height and the range of the projectile.
Materials. For the projectiles, we need marble or jackstone, soda or water plastic bottle cap, powder. Example, face powder or flour on low container. For the projectile launcher, we need a retractable pen, preferably HBW matrix pen, sticky tape, pair of scissors, and 2 popsicle sticks. For the inclined surface, we need 1/8 illustration board 10 by 15, cooking baking sheet 13 by 17 alone, 4 books 1 inch thick for 200 incline and weight support. We also need tabletop, protractor, pencil, tissue paper, and ruler or tape measure. For the activity regarding to linear horizontal motion, here's the procedure. Use the pen to move the marble horizontally along the tabletop. See that the depressed end of the pen will hit the object about the center. Observe the motion. Sketch and label the velocity time and the acceleration time graphs on the axis in your activity sheet. After you finish the activity, complete the sentence. A ball rolling horizontally has a velocity that is blank and an acceleration that is blank.